go to the position 3, and then another 90 degree, go to the origin position. When it comes back to the original position, that means that the operation has been completed. So this is how 4-fold look like. Okay. And there's no 5-fold. There's no 5-fold. And the next one is 6-fold. Okay. For 6-fold, same thing. We apply this equation. So 2 pi over 6. So 360 degree over 6. So each rotation involves 60 degree of the rotation. Okay. Each fold rotate involves 60 degree of rotation. So this is what we call rotational axis symmetry. Okay, or we call it 1-fold, 2-fold, 3-fold, 4-fold, and 6-fold. Then you may wonder why there's no 5-fold in the nature of the symmetry. Okay, there's one simple calculation that proving that there's no 5-fold axis in this world. All right, for the real crystal, there's no 5-fold. So, but I'm not going to show here because this is more to the master level. I do show in master level, but for undergrad, you just need to remember that there's only 5 types of the rotational symmetry: 1, 2, 3, 4, and 6. Okay, so for the real crystal, there's no 5-fold, but for the pseudo crystal, yes, that's 5-fold. And if not mistaken, the region, I think region here, within 10 years, there's one scientist who crystallized the 5-fold crystal. Okay, the crystal with 5-fold. So he was the first one to prove that there would be 5-fold in the pseudo crystal, and he was awarded the Nobel Prize. Easy, right, to get the Nobel Prize? Because this is a very big discovery, because in our mindset, we also have proven using the mathematic way and many ways that there's no 5-fold. And in our 230 spectrum, there's also no 5-fold axis. But this scientist, he successfully proven that there's 5-fold symmetry axis in the pseudo crystal, and eventually he was awarded the Nobel Prize. Okay, so next I'll proceed to the plane. Plane is rather simple if compared with the rotation. Plane basically just means the mirror plane. Okay, mirror plane or reflection. So whether the lattice is identical on either side of an imaginary plane. So here, let's say this is one mirror plane. If I have one left hand atom here, after the mirror plane symmetry, I will got the right hand atom or lattice point. But bear in mind that plane symmetry involves converting the atom or lattice point from one hand to the other hand. You just imagine that when you stand in front of the plane or in front of the mirror. So your right hand will be left hand in the mirror, right? If you don't believe, you can go in front of the mirror, and now you raise your right hand. Then you look at the mirror. It's actually the left hand inside the mirror. So for mirror plane, the origin point, if the original point is left hand, then the mirror plane generated lattice point or atom will be right hand. And normally we put this comma to indicate that this atom or lattice point is of different hand with the original one. Okay, so it's also very simple. Of course, later on I will go to more detail. And the last one, the point or inversion. So point inversion is a point exists in the lattice such that the operation R to R prime leave the lattice unchanged. Okay, the point inversion basically is a combination of rotation and mirror plane. Alright, so I will show you the picture illustrating the point inversion later on. Okay, the definition of symmetry. A symmetry operation is a process of transforming an object such that the initial and final state are not able to be identified as difference. Okay, remember just now I said that like for twofold, I have one origin lattice point atom here, and then for twofold, you rotate by 180 degree, and come to this point. So again, it will rotate 180 degree and go back to the original point. Then the twofold symmetry is complete. So this is the origin, and this is the symmetry generated point. And these 2 points is exactly the same. Okay, let's say for threefold or fourfold will be easiest to draw, fourfold. So this one will go 90 degree to here, and go 90 degree to here, and go 90 degree to here. So all these 4 lattice point or atom will be considered as same. However, for mirror plane, if I have one lattice point look like this, so after the mirror plane, it will look like this, right? So these two are exactly the same, except this is left hand, this is right hand, or this is right hand, this is left hand. So these 2 atom or lattice point should have different handedness. Okay. Okay. So this is the arrangement of the cubic system. So we have simple cubic here, we have body center cubic here, we have face center cubic here. So it looks like very simple, but in fact, it involves many symmetry inside. Okay, it involves many symmetry. Like this point to this point is involved translation symmetry. This point to this point, translation symmetry. This point to this point, it could involve inversion point, and this point to this point, translation, and so on and so on. Okay, so later on I will explain all these things. So lattice symmetry operation. There are several symmetry operations that can act on a crystal structure. Translation, T equal to N1A plus N2B plus N3C. Depends on whether you want to put it A1, A2, A3, or you want to put it ABC for the lattice vector. It's up to you. And then we have axis of plane, rotation means axis lah. Reflection means plane. For rotation, we have n flow axis, 1, 2, 3, 4, and 6 fold. And then for reflection, we only have mirror plane. Okay, and then we also have inversion center. And then when you combine 1, 2, and 3 randomly, let's say you combine translation